It is my absolute pleasure to introduce Dr. Marcia Rieke. She is going to be presenting James Webb Space Telescope, past, present, future, I guess. I'm very excited about this presentation because although we all love Mars, and Mars is the first step in making humans a spacefaring civilization, I like to think about humans to Mars as a bridge to the stars, and hopefully the Webb telescope will get us to the stars. Dr. Rieke.
So good morning, everyone, and thank you very much for inviting an astronomer to come talk to you all. And of course, those of you that know the history of my home institution, Stewart Observatory, know that we have a very interesting connection to Mars because our founder was kicked out of Flagstaff because he couldn't see the canals. So there's all sorts of good connections here. So I want to tell you about a project that is an international collaboration and shows several things. First, it shows that 14 countries can come together to achieve something spectacular. And it shows that people can take risks and make very complicated things happen. It's hard to judge whether this mission is more complicated than a Mars sample return or not, but this mission has the Webb telescope has a lot of complication to it. And before I get on to some of that complication, I just want to comment on this image that's up right now. This is one of the early release observations that was taken to highlight the capabilities of the telescope. And I have to tell you, in a sense, this is a fake image. I don't mean fake in the spatial sense, but fake in the following sense. This Webb telescope senses infrared light. It can actually sense maybe the very reddest wavelengths that your eye can see if you put the right filter in. But this image is a fake in terms of the coloration. And the top part of the image that looks like sky is indeed rather devoid of interstellar material, and because the bright newly formed stars have destroyed that material. And the bottom part of the image that looks like a cliff or something is colored brown because it's emitting different wavelengths primarily, and it shows where dust and gas are. And so there's a certain artistic part to this image that the false color is what makes it visually interesting. And eventually we will all go through and find all kinds of very interesting artifacts that give us clues about how the star formation process works in this kind of picture. See if I can, whoops, that's not good. There we go. So a lot of the complication with this mission has to do with being a telescope that has to fold up into a rocket nose cone. And our launch was last Christmas morning. What a wonderful Christmas present to finally get there. And an even greater present was the first couple of weeks of the mission where everything unfolded and deployed properly. There were many single point failures in here. And even as recently as a couple years ago, there were people telling me, why are you wasting your time on this mission? It'll never work. Well, obviously it did work, and it worked because we practiced, rehearsed, and we got it right. And the telescope is out at L2, so the telescope is 4 times further away from the Earth than the Moon. And so there, at the moment, we don't have any way to service it. We had to get it right the first time, which was part of the reason that we did all of the action with rehearsing. So for those of you that don't live and breathe James Webb Space Telescope every day, and this gives you a little bit of an overview. The primary mirror is comprised of 18 separate segments, which enabled it to be folded up. And these can be each one adjusted so that we can make these 18 segments work as though they are a single, smooth, perfect, nearly perfect mirror. And another very important thing about this mission is that it operates only 40 degrees above absolute zero. That's because it's an infrared telescope. We don't want heat to bother us. And I'll show an example of how that works. And the people at Ariane Space who launched us did such a wonderful job with their orbital mechanics and getting everything right that we had a lot of fuel left when we got to L2, and we can actually do station keeping there, not for the 5-year requirement, but it looks like we could last for 25 years. And so we now have to hope that our cryogenic mechanisms and the instruments and so on last that long. But an amazing story. So I said that we need to cool the telescope. You can see a guy here standing in front of a blast furnace, probably refining some iron ore, and he's holding a match. But I think you'll agree it's rather difficult to see the match. But if we can get rid of that blast furnace, suddenly the match becomes much more visible. And if we were to try to do, and I have tried before we had infrared space missions, to do infrared observations from ground-based telescopes. And the heat from the telescope and the atmosphere make it very difficult to see anything faint. But if we go to space, we can cool the telescope. Can't do that on the surface of the Earth because the atmosphere and water would freeze out and mess up the optics. But in space, you can cool the telescope far more than you ever could on the surface of the Earth. And that lets us see the faint targets of interest. And you'll see that what we're interested in doing is finding the most distant galaxies. That's a project aimed at trying to understand more about the laws of physics that operated early in the history of the universe and that helped galaxies and like our own Milky Way form. And another big goal now is to do an inventory of exosolar systems to understand more about the distribution of planets around stars. What are the characters of those planets? Can we find ones that show evidence of having the right mixture in their atmospheres, that they might be habitable? So we're very much into searching for life. So one of the key things about making Webb work was testing it ahead of time. And I call it the Peripatetic James Webb Space Telescope. We started out at Goddard Space Flight Center, where we tested the instruments, and we bolted the instruments onto the telescope, but we couldn't test the telescope with the instruments there because it was too big. We had to go to Johnson Space Flight Center, where we did a very elaborate cryogenic test, and I'll show a picture. Part of the excitement of that test was that Hurricane Harvey struck during the middle of our test, and we kept going, and the telescope was always safe because it was in this lovely big chamber I'll show you a picture of. We were less safe, but no one got hurt, thank goodness. And after that end-to-end optical test, we took everything to Northrop Grumman, just a little ways south of the airport in Los Angeles. And that's where we made it to the spacecraft in the sunshield. Then we got on a boat, went through the Panama Canal, and reached to the Kourou, which is where the Ariane Space has their launch center. And the major European contribution to the mission was this launch vehicle. So this is the chamber that we used for our big test. This test was conducted at as low a vacuum as we could achieve, which was actually very good. And it was done at the 40 Kelvin temperature that we would be operating in space. And this chamber was not built for Webb. It was refurbished for Webb, but it was originally built to test the lunar rover. So a very interesting confluence of the manned space program and an astronomy space program. And you can see in the sort of computer drawing on the left-hand side there, what the telescope looked like inside that chamber. And we had a lot of optical test equipment in there too, so that we could inject simulated stars and test the telescope alignment system. And I have to say the people at Johnson were just fantastic in helping us they had to do a lot of stuff when Hurricane Harvey hit. They had a hurricane plan, and there were issues for us, things like grocery stores and restaurants were closed during the hurricane, but yet we wanted to keep the test going, and so they helped facilitate us not starving to death while we're testing. So we got through all of that, and the telescope was transported to Northrop Grumman. You can see a picture here of the telescope being mated to the, at that point, not deployed sun shield. And you can see some cabling sticking up because the underneath side of the sun shield is where the main spacecraft housekeeping facilities reside for Webb. And those cables carry everything up to the instruments that are on the back side of the telescope and just as cold as the telescope. And that includes some special stuff for MIRI's cryo cooler. The mid-infrared instrument has detectors that operate at only 7 degrees above absolute zero. So once we got on orbit and everything was deployed, we then had to align the telescope. And we started doing that when my instrument NIRCam reached 100 Kelvin, which was when we could start sensing light. And the engineers had predicted that the 18 segments might be kind of pointing higgledy-piggledy from the launch vibrations, and that the images of the 18 segments could be spread out over an area nearly as large as the full moon. So we plan to take data over this blue, what looks like a blue grid, which is actually outlining a whole series of over 1,500 NIRCam exposures to make certain that we would find all the images from all 18 mirror segments. So the way this works is you point at a star, but you see it 18 times because each segment operates as though it's an independent telescope till we get it lined up. Well, luckily, you can see this area now that looks like a little black rectangle. These segments were found over a much smaller area, and that was one of the first clues that this whole alignment and telescope operation was going to go more smoothly than we had predicted. Oops, I did that again. I'm not very good at, okay, here we go. So the first thing was to go through that initial image where you can see if you count them, there are 18 separate star images. We had to identify which segment matches to which image so that we knew who to operate when we were trying to get things aligned. And so we had to correct the quality of the tip and tilt of those segments. And then we also had to eventually drive them together into being stacked up on top of each other. And then we had to go through another procedure called phasing so that instead of having a step function between the two segments, they would be exactly at the same focal distance. And that took several months because we did it very carefully, following a very set procedure so that we wouldn't do something that would make it more messed up than it was to begin with. And so we ended up with an absolutely gorgeous telescope alignment image. This was of a star that was just conveniently located in the viewing zone. The telescope can only see 40% of the sky at any one time because the sun shield has to be kept pointing at the sun so we don't warm up. And it was also a nicely isolated star. And so it was perfect. And this alignment evaluation image proved to be that the point spread function revealed that the telescope not only met the requirement of being what we call diffraction limited at 2 microns, kind of 4 times visible light, it's actually diffraction limited at 1 micron, just twice visible light. And so when you look at the Webb images, you're going to see more detail than you see from Hubble, even though it's working at a much longer wavelength because the alignment is perfect. And this alignment image had an interesting bonus. One of the wavefront sensing guys went through and looked at the background and found galaxies all over the place, even though it was a relatively short image. And we should have known that this would happen because the near infrared wavelengths that my camera works at are where the output of galaxies, even quite highly redshifted galaxies, peak. And so it's quite straightforward to see galaxies with Webb. And one of the kind of jokes that came out, if you remember the episode where the French man put a picture of chorizo on the Webb and on the WEB in Webb, said that this was a Webb telescope picture, and people tweeted right away, no, this can't be a real Webb picture because there are no galaxies in the background. So for those that like plots and tables, I mean, the optical performance of this telescope is just fantastic. And people have sometimes wondered about whether or not that micrometeoroid hit. We have an open tube telescope, nothing shields us from solar system debris, whether that was going to cause, wreck the images. Well, one way to look at this, you may not understand the concept of a wavefront error, but that's one way to quantify the optical quality. The requirement was to be at 135 nanometers, and the first alignment achieved 50, more than twice as good as the requirement. And after the micrometeoroid hit, we were able to adjust the segment that got hit. You can just barely see next to the image of the secondary mirror strut. You can see the little dent. The wavefront error only degraded to 60 nanometers. And so it was scary, but we could work around it. And we hope there aren't too many more like that. The general rate of getting hits is just what the people at Marshall have predicted. And this particular hit that made the little dent was much bigger than anyone had expected we would see. So the combination of high sensitivity and large telescope is just leading to all kinds of spectacular results. And this just compares an image from the previous excellent infrared mission called the Spitzer Space Telescope with basically the same wavelength, what we can do with Webb. And you can see that the improvement is absolutely stunning. And that's partly because Spitzer, as great as it was as a mission, its primary mirror was smaller than one of Webb's 18 segments. And so we have a great leg up on Spitzer. So I mentioned that one of the goals, in fact, the original way this mission was sold was to find the first galaxies that form. And we're hoping to get back to within maybe 100 million years of the Big Bang. And we just have received our first big pile of deep survey data. My crew back down in Tucson are busy analyzing that, and we're going to be able to find some very distant galaxies. And one of the I must not press too hard or I get one of the early release observations was this of a lensing cluster, which you can see the gravitational lenses as what in this image look like reddish arcs are surrounding this rather fuzzy elliptical galaxy. But if you compare this image to one from Hubble, you will find galaxies that Hubble didn't see. They are so redshifted that you needed to go into the infrared to see them at all. And President Biden released this images. We were quite surprised that he took this much this much interest in a NASA mission, and that was very heartening. One of our other big research frontiers is characterizing exoplanets. And the way we intend to do that is mostly by the transit method, where if you difference the signal between when the planet is eclipsing the star and when the planet is hidden behind the star, you can then see the effect of the planet's atmosphere. You can see how much of the starlight it absorbs. And here's one of the first spectra that was of what we call a hot Jupiter. The star that this particular exoplanet is orbiting is a star quite similar to the sun. What's not similar is that this planet is orbiting at a distance from this G star that's only 1/9 as far as Mercury is from the sun. So when we label water in here, think your mental image should be really like steam. I mean, it's water molecules, but very hot. And we call this a hot Jupiter. And more recently, another one of these hot Jupiters, also orbiting a solar-like star at a distance much closer than Mercury is to the sun. We discovered carbon dioxide, and this is the first detection of carbon dioxide on a planet outside the solar system. And of course, this is a very common molecule on Mars. And so we can now start to understand climates and heat transport and things on some of these exoplanets. And that will be an interesting activity all of its own. I like to get next instead. The holy grail for this part of Webb's mission is to find a spectrum that looks like this. And this would be one that would combine data from several of our instruments. And this is what an Earth-like exoplanet's transmission spectrum would look like. And Earth-like planets, being small, don't blot out as much of their parent starlight, so they're going to be a much more difficult target. But there are already observations on the planning schedule to try to do this. And I think it'll be really exciting if we find something like this. And people sometimes ask, can we prove that there's life on such an exoplanet? And I'm reluctant to say, yeah, we can, because if you go and ask our biology friends, if we say, if we see this, this, and this, does that prove that there's life there? And the answer always is, no, not really. And so what would be a biomarker is still a matter of some debate, but we're certainly going to be able to do a census of exoplanets and see what are common types of atmospheres and so on, which should help our understanding. We shouldn't forget that the Planetary Sciences Division at NASA paid for the ability of Webb to track solar system targets, and there are quite a number of solar system observations planned. Here are a couple of results from the first two. You can see Jupiter and the best view of Neptune and its rings that we've had in a very long time. And you can see some of Neptune's friends. And we can also see the ring and some of Jupiter's friends. And I couldn't come to the Mars Society without pointing out that we've actually pointed Webb at Mars. Mars is a challenging target, not for the reasons that you would think. The reason it's a challenging target is that it's very bright at our infrared wavelengths. And that's not to say we won't learn something different from what we would learn by observing with the ground-based telescope, because we can observe at wavelengths you can't do from the ground. But you have to use subarrays and take little postage stamps if you want to move across the surface. But you can see that it is possible to observe things, get pretty good spatial resolution, and I think we'll see in the future that we can actually learn something even about Mars, something as close by as that with Webb. And I will close with an image that was released just yesterday of the Pillars of Creation that was done by HST a long time ago. If you blow up the JWST image, you'll see much more detail. And if you look very carefully, you will see some scarlet regions at the tips of a couple of the pillars. That's where we're seeing ionized hydrogen emission, where new stars are forming that were completely invisible to Hubble because they were hidden by gas and dust. So stay tuned. We're just getting going on this mission, and thank you very much.
Questions?
Other than an accident such as getting hit by a meteorite, what would determine the durability, the length of life? Is it the ability of the propellant or battery power or any parts that we know wear out from testing?
The first limitation is the propellant that keeps us at L2. And when that runs out, we won't be able to control the telescope's positioning anymore. And that's the 25-year estimate. Cryogenic mechanisms, they were all tested against a 10-year lifetime. And so if you know how engineers are conservative and they always make things that are better than what you thought, I suspect that our cryogenic mechanisms will make it for 25 years, but that is a worry because we know that ball bearings in a cryogenic environment where you can't have the usual kinds of lubricants can wear out.
Hello, you mentioned the questions around a list of biomarkers in the signals. Is there a list of questions for techno markers?
There is a list of techno markers, and I think there is again a question about would it be an unambiguous techno marker, or is there some yet other geologic process that would get us? I mean, a good example are PAH is polyaromatic hydrocarbons, which are put out as a form of pollution from cars and things, but there are also geologic processes that make that. But I think there's some better biomarkers than that. I mean, techno markers than that.
Hi, Stelly now in the Philadelphia chapter. So you mentioned that Earth-like planet atmospheric spectra are on the observation list. Do you have any specifics on which and when?
I think sometime, I don't know exactly when in the next year and a half, but one of the exoplanets that was discovered by the group from Belgium, and I'm drawing a blank on their name right now. They name stuff after one of their beers, but it's one of the TRAPPIST. Thank you. Yes, one of the TRAPPIST, and I don't remember which one, but you can actually look on the Space Telescope Science Institute planning page and probably find out which one.
Hi, my question is, how do you detect the micrometeorite impacts?
We detect it two ways. One way is that after them, the wavefront error goes way up, and every 2 days we are monitoring the wavefront error of the telescope because the segments do tend to drift apart. And so when there's a micrometeorite hit, you'll see one segment that's been jiggled out of position a little bit. And we can put in a special lens that NIRCam has that changes the focus from infinity to being able to look at the primary mirror, so we can actually see the results of those hits.
Thank you very much.